Hello everyone, today let's solve the problem Sonya and the Informatics, right? So this was asked on the code forces round 553 for the division 2, right? So let's go with the question. So let's see what the question states. You can just go through the question, it's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem, right? So here what the question states, we are given a binary, this one array A. I'll just come here 1 second. Yeah, we have been given a binary array A of length n, right? So we can randomly choose k pairs here. We can randomly choose k pairs here, right? K pairs in the sense we can consider the pairs I comma j, right, uniformly, and we can swap a of I and a of j each time. We can swap a of I and a of j each time, right? So this is fine. We have to find the probability that after k swaps the array becomes non-decreasing, right? So we have to find the probability that after k swaps the array becomes non-decreasing, meaning all zeros then ones, right? So we have to output the probability modulo 1e9 plus 7 or 10 to the power of 9 plus 7 as p into q to the power of -1 mod, right? So if probability is 0, then we have to print 0. So this is also important. If probability is 0, then we have to print 0 as well. If probability is 0, then we have to print 0 as well, right? So let's I'll just read the question out loud. You can just listen to this again, right? So we have been given a binary array A of length n. So we will be seeing the binary array within the input. So we have been given the binary array A of length n. We have to randomly choose the k pairs I comma j, right? I less than or equal to 1, this one greater than j, and j less than or j less than I and j greater than or equal to n, right? So this is fine. Now uniformly and swap a of I and a of j each time, this one, right? So we have to find the probability that after k swaps the array becomes non-decreasing, all zeros then ones, right? So we have to output the probability modulo 10 to the power of 9 plus 7 as p into q to the power of -1 mod. If probability is 0, then we have to print. So this is the question, right? So let me delete this one. Yeah, let's come to the input output part. So we have 3 to this one, just give me a second here. Yeah, we have 3 2 and 0 1 0. The output that we need to get here is this one after applying the modulo operation. Modulo value we have been given 10 to the power of 9 plus 7, right? So here within the example, let's consider the first example for the approach. I'll just explain the approach here itself for this particular problem. So n we have been given 3 here. See here, this one, this is nothing but n we have been given 3 and array we have been given this one, this is nothing but the array, right? 0 1 0, right? So c we have been given 1. See this one, c we have been given 1. Last c position is index 3, meaning initial st nothing but st equals 0, right? No ones in the last position. So now states are I equals 0 and I equals 1. States are I equals 0 and I equals 1, right? So before this one I want to tell you one thing. So we'll be going with the dynamic programming, right? So we'll be going with the dynamic programming to solve this particular problem, right? So first denom will be 3 pairs, right? So first denom will be this one. I'll just consider here denom. This one will be 3 because we have 3 pairs, right? So from I equals 0 up to c minus I to the power of 2 by denom equals 1 by 3, right? Down will be initially 0 and stay will be 2 by 3, right? From I equals 1 down will be from I equals 1 down will be equal to 1 into 3 minus 2 plus 1 by 3, right? So this one will be 2 by 3. Down equals 2 by 3 and stay will be 1 by 3 here. Stay will be 1 by 3, right? So let's consider this one dp. So let's do the dp for k equals 2, right? So let's do the dp for k equals to k we have been given 2 here, n we have been given 3 and k we have been given 2 here, right? So we have to do the dp for k equals to after one swap. So dp will be after one swap, dp will be this 2 by 3 comma 1 by 3, right? So after 2 swaps dp would be, so let's consider for the 2 swaps here. After 2 swaps dp will be this one, 2 by 3 into 2 by 3 plus this one, 1 by 3 into 2 by 3. This is fine. This is fine. We have to compute final dp, right? So final dp of 1 equals 2 by 3 into 1 by 3 plus 1 by 3 into 1 by 3. So final dp would be this one. I'll just write here. Final dp would be 1 by 3 itself. Final dp would be 1 by 3 because dp of 1 would be 2 by 3 into 1 by 3 plus 1 by 3 into 1 by 3, which will lead to 1 by 3. So we have to do, so we have got the solution 1 by 3 here. We have to do 1 by 3 modulo this one, 10 to the power of 9 plus 7, right? 10 to the power of 9 plus 7. So that will lead to the output, this one, 1 by 3 modulo this one, what do we call, 1 by 3 mod 10 to the power of 9 plus 7. The output will give us this one. What do we call? Basically, rather than writing, the output will give us this one, right? Ending with a 36, right? So the output that we got here matches the output that they have given for the example 1 or the input 1 within the question. So our approach works absolutely correct in this case, right? As we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part, right? So here one more thing before we hop into complexities part. So we will be doing rolling dp for the small k, right? For the large k, we will raise the transition matrix to power k, right? Nothing but the matrix exponentiation. We'll be going with the number theory. Basically, we'll be going with the matrix exponentiation and multiply the initial vector for the large k, right? So it is same as mathematically same dp, but it will be faster, right? It will be faster compared to normal dp. So this is it about the this one approach, right? So what will be the time complexity and the space complexity here? The time complexity would lead to this one. What do we call? Building, we are going with a S into S matrix, right? So building S into S matrix would lead to pico of S to the power of 2, right? It will be S square. So dp simulation would take because m into s to the power of 2, but implemented as m into s using space no loops, right? And matrix exponentiation would take big of s cube logarithmic m for the large m, right? So overall, for the time complexity for building S into S matrix would we can consider big of s square, right? This is fine. What would be the space complexity? Space complexity would lead to big of s square as well, because this one will be making use of the transition matrix plus big of s for the vector. So overall space complexity would lead to big of s square as well. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of s square and big of s square respectively. Now as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code, right? Now first we'll be making use of the fast input and output, right? So for that I'll just come to the compiler. Let's import here input output package, right? Also we'll be making use of the different utilities, so I'll just go with import java.util.start, right? So let's do one thing. I'll just go with class main, this one. This is fine. So within the main class, let's consider the modulo value, right? So we have to go with the 10 to the power of 9 plus 1, 9 plus 7, right? So we have to use this one for all the modular arithmetic. So I'll just go with here static final int mod equals 7, right? 8 zeros followed by the 7. This is fine. Now what we need to do, let's go with the fast modular exponentiation, meaning we will be returning a to the power of e modulo mod, right? So let's go with the fast modular exponentiation. So I'll just go with static here and so this one long a long e. This is fine. Now so within the modpo this one helper method, So let's go with the accumulate of a result, right? So I'll just go with long r equals 1. Also let's go with a equals a modulo mod. So this one will be just mod actually. This is fine. Next step would be, let's go with the simple while loop, meaning we'll be going with a binary exponentiation loop, right? So I'll just go with while here. So this one e greater than 0. Let's go with simple if condition. If current bit is 1, then we have to multiply, meaning, so I'll just go with if e this one and 1 bitwise and 1, so this is equivalent to 1, r equals r into this one a modulo mod, right? So this is fine. Now let's go with the square base. A equals, so this one will be a into a modulo mod. So this is fine, man. Now let's go with the shift exponent. We'll be going with a right shift actually, right? Shift exponent right, basically in simple terms. So I'll just go with right shift operator equals 1. This is fine. Now the final step would be this one. We have to cast to this one int. Mod fits in the int, right? So we can just keep here return int. So we are just going accordingly with the constraints here. So I'll just come out of this one entirely. So now I'll just go with the multiplication matrices helper method, meaning we have to multiply two matrices A and B modulo mod. So we'll be making use of the square matrices, right? So here we'll assume the square matrices. Basically I'll just go with static here int multiplication matrices. So this one I'll just go with A. Also I need a parameter B as well. So this one will be B. This is fine. So within the helper method multiplication this one matrices, first we have to go with the matrix size. So we'll be making use of this one int n equals a dot length, and so this is fine. The next step would be let's go with the result matrix. When I say result matrix, so this one will be C equals new int of n, and this is fine. So the next step would be, let's go with a simple two for loops, right? Nested loops. We have to iterate rows of A. Also we have to this one skip zeros for the speed using another for loop. So we'll be going with the this one I as well as the k, right? So we have to iterate rows of A first. So for that one I'll just go with for here this one int I equals 0, I less than n, so I plus plus. Within the for loop we have to skip the zeros for speed, so I'll just go with a for int k equals 0, k less than n, so this will be k plus plus. So within this for loop, so we have to take a of ik as long to avoid the overflow. So this one will be long ab a of I k. This is fine. Now let's iterate the columns of B. Also let's skip the zeros and B row, and we have to accumulate. First let's iterate columns of B. So this one will be for j equals 0, j less than n, j plus plus, right? So this is fine. So within the for loop, let's skip the zeros and B row. So this one will be if B of k, this one j not equal to 0, then what we need to do, so this one we have to accumulate, right? So this one will be C of ij equivalent to, so let's go with int here. Int is enough basically. So this one will be C of I j plus av into bk. So this is fine. So not bk basically. We have to represent this one within the array, right? So b of k, b of kj, this is fine, modulo, let's give mod here. This is fine. After successfully accumulating, then what we will do, So I'll just come out of this one. So we will be returning C, meaning we have to return the product matrix, right? So I'll just go with return C, right? So this is fine. Let me come out of this one entirely. Now let's go with a multiplication vector matrix, right? So this one here will be going with a multiply row vector, this one VEC by matrix M basically, right? So this one, let's see that one in the action one. So let's go with the helper method multiplication vector matrix, right? So I'll just go with static here. So this one is fine, int. So this one will be multiplication vector mat. So this one will be int vector. So this one will be int. So this is fine, m, right? So this is fine. So within this helper method, let's go with a matrix dimension first. So I'll just go with int n equals m dot length. Also let's go with the result vector, nothing but the initialize 0. So this one will be int result equals, so new int of n, right? So let's go with the iteration part for each entry in the vector. So I'll just go with for here int I equals 0, I less than n. So let me go with I plus plus. So within the for loop, what we will be doing, we have to skip the zeros first. So I'll just go with if vector of I equals 0, then what we will do, let me give continue here. We are skipping zeros right here. So let's go with a value as long for safety. So in the sense, I'll just give here long b equals vector of I. So this is fine. Now let's go with a for loop. So we have to distribute to the result using m row. So this one will be for, this one will be int j equals 0. So this one will be j less than n, and we have to increment the j as well, j plus plus, right? So this one will be if, so this one has to be m of I j, this one if not equal to 0, then result of j, this is equal to, so let me give int here, this is also fine. So this one will be result of j, this is fine. So this one will be plus v into m of, this one will be I, this one will be j basically, right? So this one will be j, finally modulo mod. So this is fine. Now let's do one thing, we have to return only answer. We are left with returning answer, so I'll just return answer here, right? So let me come out of this one entirely. So we are done with the multiplication vector matrix helper function. Now we'll be going with this one matrix power, or we'll be going with the fast exponentiation of matrix base to the power exponentiation. Base is nothing but n into n here. So let's go with one more helper method here, matrix power. So this one will be static int. So this one will be mat power. So let's go with the parameters here. First one will be base. So this this one will be base, and also long exponentiation, right? So this is fine man. Now within this helper method, let's go with the dimension first. So this one will be n equals base dot length. So this is fine. The next step would be, so we have to go with the identity matrix to accumulate the result. So this one will be int result equals, so this one will be new, just give me a second, 1 second here. So this one will be new int of n and m, right? So let's go with the simple for loop here. We have to set the identity. So I'll just go with for here int I equals 0, I less than n, I plus plus. So this one I can just set this one result of I, let's assign this one to 1, right? So we have set the identity. Now let's go with the simple while loop, nothing but the binary exponentiation loop for the matrices, right? So I'll just go with while. So this one exp, this one is greater than 0. I'll just go with the simple if condition here, exponentiation bitwise and 1. If it is equal to 1, then result we will be assigning this one to the multiplication matrix, this one helper method, result comma, let me pass base as well. Right, so the next step would be, let's assign the base to multiplication matrix. So let's pass base twice here, base comma base. So this is fine, man. Now we have to shift the exponent, in the sense I'll be making use of the right shift operator here, this one equivalent to 1. So finally we have to return the base, this one, to the power of exponent, right? So in the simple terms, I'll just go with result here, or we'll just return the result here. This is fine. Now we are done with 3 helper methods that we wanted, right? So let's do one thing. Let's quickly go with the this one, main method basically, right? So this will be huge. So I'll just go with main here. So let me delete this one. So here let me include throws exception, right? So within the main method, so I'll go with buffered reader, right? Buffered reader br equals new buffered reader. So this one will be new input stream reader system dot in. So I'll just go with a print writer output equals new print writer new buffered writer. So this one is fine. Output stream writer. So this is fine. System dot out. So this is fine. Now let's go with the string tokenizer as well, because we have to read the first line tokens, right? So for that we'll be making use of the string tokenizer, man. So I'll just be going string tokenizer. We have already made use of st, so I'll be making use of s_t here, right? So this one will be new string tokenizer buffered reader dot read line. So this is fine, man. Now after going with the string tokenizer, we have to read the array length, as well as we have to read the number of random swaps, that is k in the statement. So these things, right? So in the input, this one 3 and 2 read n and k basically in simple terms. So this one will be int n equals, both are integers, right? So this one will be integer dot %, string tokenizer not. So I'll just go with next token here. Next step would be, for the k we'll be considering this one. Let me consider m instead of k. So I'll just go with long dot parse long of this string tokenizer dot next token. So this one will be next token. This is fine. So this is fine. Now let's go with a one indexed array of that will be a of 1 to n, right? So this will be int array equals new int of n plus 1. This is fine. So this will be int c equals just give me a second, sir. Int c equals 0. When I say int c equals 0, we are going with the total number of ones in the array, right? So we will be going with total number of ones in the array. So initially I have initialized c to 0, and also let me initialize the index to 1, right? So the current index, this is nothing but the current index to fill. Now let's go with a while loop, meaning we have to read the possibly multiple tokens per line, right? So for that this one index has to be always less than or equal to n, right? So I'll just write here while index or is less than or equal to n. Then we have to read the next input line. So this one will be string tokenizer, this one t equals new, this one will be string tokenizer buffered reader dot read line. So this one will be, so let me go with a while loop here. So this one t has I'll just go with has more tokens. So I'll just go with has more tokens and index less than or equal to n, then what we will do, while tokens and positions remain, right? So then we have to store the element within the while loop, and also we have to accumulate the count of ones and move to the next index. So I'll just go with a of index equals integer. So this one will be parse int, not the long, basically parse int. This one we have considered t, variable name t dot next token. It's just storing the element, then we have to accumulate the count of ones, meaning here c equals c plus a of index. Next finally we have to move to the next index, meaning so we have to increment the index. So this is fine. Let me come out of this one entirely. So first what we need to do, let's go with the st. I'll initialize this one to 0 because st is nothing but initial number of ones among the last c positions, right? So I can just write it on this way. C is equal 0. Let's go with the iteration part. So we have to go with sum of this one, a of n minus c plus 1 to n. So this will be for loop. So int I equals n minus c plus 1, I less than or equal to n, I plus plus. So this one will be st equals st plus a of I. This is fine, man. So let's go with the total number of the unordered pairs modulo mod, right? So I'll just go with, so I said denom, right? So variable denom I used in the approach, nothing but this one, right? So I'll just go with long. Let me make use of the variable denom, basically denominator. So this one will be denom. So as we have made use of the long, I'll just go with 1l into n into this one, n minus 1 by 2 modulo mod. So this is fine. So this is nothing but the total number of unordered pairs modulo mod. Next we have to go with the modular inverse of the denom, nothing but, so here we'll be going with the format little theorem, as everywhere we are going with a modulo this one, modulo inverse, this one number theory, right? So modulo inverse, so usually we'll be going with the format little theorem, right? So mod minus 2, if you remember, if you know the theorem, this one will be inverse denominator. So this one will be mod power, so denom mod minus 2. This is fine. Now let's do one thing. Let's go with the minimum possible ones in the last three positions, meaning, so I'll just go with int l equals math dot max of, so this one will be 2 into c 2 into c minus n comma 0. This is the minimal possible ones on the last three positions. Next we have to go with the number of possible states, meaning I equals L to C, that is inclusive. So this one will be int S equals C minus L plus 1. This is fine, man. So the next step would be, if there is only one state, that is nothing but S less than or equal to 1, the chain is trivial here and we have to stay where it starts, meaning let me write the simple if condition here. If S less than or equal to 1, we have to go with only one state. Here this one will be out dot println. So this one will be out dot println of 1. This is fine. So this is just the probability to be sorted on 1, right? So this is already fixed, man. We don't have to worry about it. So I'll just go with out dot flush or out dot close. You can just go with flush or close, anything. So I'll just go with out dot flush here, and finally we don't have to return anything in this case, so I'll just make use of the return keyword term. We are just exiting here, right? So I'll just give here return. So next what we'll do, let's do one thing. Let's build a transition matrix M of size S into S, if you remember the approach, right? So we'll be going with a mapping in the sense we'll be going with a state I, nothing but the actual count, to the index idx equals I minus L. So this index is 0 based, just remember this one. This is not 1 based, this is 0 based index. So I'll just go with int M equals new int of s. This is fine, man. So let's go with the iteration part for int I equals L, I less than or equal to C, I plus plus. So within this for loop, what we'll be doing, for each possible I, we have to convert the state value to the matrix index. So this one will be int index I equals I minus L. This is fine. Next, after converting the index state value to the matrix index, so let's go with the accumulator for up plus down probabilities, right? So I'll just go with long result equals 0. Now if it is possible to increase once in the last segment, then we'll be going with the formula for DP. So let's check if it is possible to increase the ones in the last segment. So I'll just go with if I plus 1 less than or equal to C. So I'll just go with here long. So we have to go with the formula for up, right? So I'll just go with 1 L as we have made use of the long here. So this one into C minus I again into this one again C minus I. This is also fine. We have to use the modular value, right? So as they have mentioned in the question strictly. So this one will be mod 2, like I'll just go with a, so I'll just make this one capital T, inversion denominator. So this one, let me make this one here as well, capital D. So we went with the format little theorem, right? So this is fine, man. I'll just go with mod here. So this is nothing but the formula for up, right? So now let's go with the transition to I plus 1. In the sense, I'll just go with M of index I, this one again index I plus 1 equals, so I'll just go with int of up. So this is fine. This is transition to I plus 1. Finally we have to accumulate. So this one will be result equals result plus up. So this is fine, modulo M word. So let me come out of this one entirely. So now if it is possible to decrease once in the last segment, then we'll be going with a formula for the downwards, right? So we have already went with the up, so we'll be going with the downwards now. If it is possible to decrease once in the last segment, so let's write the simple if condition. So this one will be if I minus 1 greater than or equal to L, then what we will do, let's go for the formula for down. So this one will be long down equals 1 L into I into, so this one will be n minus 2 into C. This is fine. plus I, right? So this one will be modulo mod. So this one will be inversion denominator. So this one will be modulo mod. So this is fine. Now let's go with the transition to I minus 1. So this one will be index I. This is fine. Index I. So this one minus 1 equals int of, so this one will be down. This is fine. This is nothing but the transition to I minus 1. After that we have to accumulate, right? So I'll just go with result equals within the braces result plus down here we have to make use of the mod value strictly. This is fine. Now let's go with the stay. I had made use of the stay variable within the approach as well. So we have to go with the remaining probability, that is to stay in the same I. So I'll just go with the long stay equals, so this one will be 1 minus result plus mod. So mod, this one will be mod. This is fine, modulo mod, right? So this is fine, man. Now let's set the stay probability. In the sense, I'll just go with again M of index I twice basically, right? So this is fine, equals, let me go with the int, let me call stay here, This is fine. We are just setting the state probability here. Let me come out of this one entirely. Now we'll be going with heuristic threshold. When I say heuristic threshold, if m is small, then we'll be doing the rolling DP. This will be big of m into s basically. Else we'll be going with a matrix exponentiation. So we have written this one. What do we call helper methods already, right? Let's move on with the this one, a heuristic threshold basically. First, we have to choose safe upper bound for the straightforward DP, right? So I'll just go with long here. Let me go with threshold, this one, threshold steps. Long threshold steps equals, so let me go with 5, some big value, right? So for the safe upper bound accordingly with the constraints, so we can go with 5 zeros here, this one followed by this one L, as we have made use of the long. So this is fine, man. Now let's do one thing. If small m, this one, we have to do the repeated DP steps, right? So I'll just go with if m less than threshold steps. So then what I'll do, this one, we will be going with the DP vector for the current step, nothing but the probabilities modulo mod, right? So this one will be int, so DP it's new int of, so this one will be s. Let me pass the s here. So this one, next step would be, let's go with the initial state, that is st, nothing but probability 1. So this one will be DP st minus L, right? So this one, let's assign this one to the 1. This is fine, man. Now let's go with the next step DP vector. So this one will be int and DP. Let me assign this one to the new int of s. This is fine. Let's move on with the iteration part, nothing but the for loop. So we have to apply the transitions m times, right? So I'll just go with for here. So this one will be long step equals 0, step less than m, so this will be step plus plus. So within the for loop, what I'll do, let's reset the next DP, meaning I'll just go with arrays dot fill of this one, what do we call, n DP comma 0. This is fine. So we have reset the next DP. Next, let's go with one more for loop for each state. So I'll just go with for here. Int s equals 0. This one will be s less than s, also s plus plus. So this is fine. So within the for loop, let's go with the current probability at the state s, meaning, so I'll just go with current variable here, and let me assign this one to the DP of s, right? So we have to skip the 0, this one, probabilities as well. So I'll just go with if current, so this one is equivalent to the value 0, then we have to skip. I'll just make use of the continue keyword within the Java, right? So now we have to distribute current according to the m of s into row, right? So this one, let's move on with the iteration part. So this will be for int t equals 0. This is fine. T less than s, so this one will be t plus plus. So this one will be if m of s t, this is also fine. If it is not equal to 0, this one will be n dp of t equals int, this one is fine. So this one will be n dp of t, this is also fine. 1 second, yeah, I'll just go with plus here, one more parenthesis, current into 1l into m of, so this one has to be m of s into t, right? So this one I can just write it on this way, m of s, this one will be t, this is fine. Yeah, this one will be modulo let me go with mod. Also again let me go with mod. So this is fine, man. Now let me come out of this one entirely. So let's go, or let's swap dp and ndp references, meaning rolling arrays, right? So this will be int dp, right? So this one dp equals ndp. So this one will be ndp. So this one, let me assign this one to the temp, right? So let me come out of this one entirely. So we have to go with the answer that is probability to be in the state I equals c, meaning index c minus l, right? So I'll just go with out dot println here, println of dp of c minus l. So this is fine. Now let's flush the output. I'll just go with out dot flush, as well as let me return. This is fine. Let me come out of this one entirely again. So now what we'll be doing, we'll be going with a large m in the sense. So let's make use of the matrix exponentiation here, meaning we have to compute m to the power of m, then multiply the initial vector by m to the power of m, right? So this will be int. So this one will be m power. So this one will be matrix, so power m comma m, right? So this is fine. Now let's go with the initial vector. This one, 1 will be at the st minus l, right? So for the initial, I'll just go with init variable name for the initial vector. So I'll just go with init equals new int of s. This is fine. Now let's start the state. To start the state, I'll just go with init. So this one will be st minus l. Let me assign this one to 1. We have to go with the final vector that is equivalent to the init into m to the power of m, meaning I'll just go with int. So this one will be final vector multiplication vector. So this one we have already written, right? So helper method. So I'll just pass here init along with, let me pass m power. So this is fine. Final vector which is equivalent to the init into m to the power of m. Finally we have to output the probability of being in state C, and let's flush the output. We are left with only two things. We have to output the probability of being in state C, and we have to flush the output, right? So just give me a second here, 1 second. So for outputting the probability of being in state C, I can just write it in this way: out dot println. So this one we have already written final vector. This one will be C minus or C hyphen L as usual. Also we need to flush the output, so you can just go with out dot flush or out dot close. I'll just go with out dot flush this time, as I have made use of flush everywhere, right? So this is fine. Now we are done with the coding part. Before checking the code with different inputs, let me do one thing. Let me copy paste the signature starter template. So I'll just paste this one over here, and let me come here. So let me copy this one. We have to get the output this one, right? Ending with 36. Let's check the same. So we have some errors here. Oh, there are so many errors, 15 errors. So line number 45 cannot find the symbol C of ij. Where is this line number 45, right? 45 within the helper method multiplication matrix. So this is C of ij. So this C has to be capital, man. Just give me a second, 1 second. Just give me a second here. Yeah, this C has to be capital. We have assigned this one C here, right? Capital C. So let me run this one now. This error has to be gone. Yeah, again this C has to be capital as well. Line number 45. Oh, this one I didn't change here. This one has to be C as well. You see anywhere? So let's run this one again. Cannot find the symbol K. So this K has to be small, I believe, right? So this one B of K, right? So B of this one Kj. Now if I run this one, this error has to be gone. Yeah. We are left with 12 errors. Cannot find the symbol answer. Where 65 multiplication vector matrix, right? So here, yeah, I have made use of the result, I believe. So this one has to be result, not answer. Yep. Now let me run this one. So error cannot find the symbol M, line number 70. This one N, we have assigned this one to the base length. This is fine. Result, oh, this one has to be N, not M. So this one, let me make this one to N itself. Let me run this one. Now this error has to be gone. We are left with 10 errors. This is fine. Incompatible types, possible lossy conversion from long to int, where this one, line number 86, within the main method, right? So this one int n and m. So this one is fine. Integer, because integer dot pass in, because that is of the type integer within the input. So this is fine. Dot next token. This is nothing but the array length. M is nothing but the long dot pass long of this one has to be STT. This one is fine. Dot next token. This is also fine. M is nothing but the number of random swaps here, right? So number of random swaps, nothing but K in the statement, right? So this one has to be equals long dot pass long STT dot next token. This is correct itself. So what error we are getting here? Let's see this one further. This one is fine. Cannot find the symbol. Again, C has to be capital 107. So where I have written this one. So let me run this one. This error has to be gone. We are left with some 9 errors. So let's see this one later. Cannot find the symbol NDP. So this one, line number 141. Arrays dot fill. So I have considered only DP. So here I have given, oh, this BDP has to be NDP basically. Just give me a second, 1 second. So we are going with the threshold steps here, right? So this one, let me assign this one NDP, not the BDP. So now this error has to be gone as well. Yep. So error incompatible types, int cannot be converted to the int. Single array, here I have mentioned double array. Line number 161. So this one int of s, right? 161 int. So this one has to be single array. Yeah, this is the mistake I have done. And let me run this one. This error has to be gone. Yeah, we are left with only one error now. This one, incompatible types, possible lossy conversion from long to int. So just give me a second here. So yeah, this is the mistake, right? So here we are going with a long, but here I have mentioned int. So this one has to be long. So that is what it is screaming. So this, let's wait. Let's do one thing. I'll just come to the line number 86. Yeah, this one, let me consider this one long. I was not focusing on that itself. So let me run this one now. Out of bounds exception, just give me a second. So in the line number 143, what I have done, so we are assigning the current to this one dp of s, right? So this s has to be capital S. So I have given this one, this s has to be small s, not the capital, sorry. I have given this one capital S. So this will obviously give the this one array out of bounds exception, right? So let me run this one again. So this error has to be gone. Yeah, we are getting the correct output, right? So this is fine, man. Now let me go with this one. Input So we have to get the output 0. Let's check the same here. We are getting the output 0. So let me go with the final one. So we have to get the this one output ending with the 3 4, right? So let me run this one. So we are getting the output ending with 3 4, right? So this is fine. So let me copy this entire code. So let me come here, let me hit the submit button. So let's wait for some time. This is fine, man. Let me paste the code once, let me hit the submit button. I hope this works. Let's see. I hope this works for all the test cases, man. So let's wait for some time. Yeah. So this is completely based on this one number theory as well as the dynamic programming, basically, right? So you can clearly see here in the toast it is showing accepted, right? So we have went with number theory, modulo inverse, this one matrix power, right? Matrix power multiplication, this one multiplication vector matrix. So these things. So this is for the faster calculation, that's it, right? Extreme optimization in simple terms. So this seems very easy, but while implementing it's damn difficult, I wouldn't lie. So to look after writing the code or after getting the solution, it seems very easy, but to implement this is freaking damn difficult, right? So this is fine. Now they have asked us to go with the 10 to the power of 9 plus 7, right? So mod value. So I had explained this one in the approach by considering the first example, right? In simple terms, that itself we have articulated in the form of code. Nothing but we have went with the extreme optimization here rather than the approach. It was simple. How we got the solution by considering the example 1 and what are the data structures that we'll be making use of and other stuff, that's it, right? It was very simple, but while writing the code we went with the extreme optimization for this particular problem, right? Constraints are very tight for this particular problem, so we went with the this one number theory along with the this one number theory algorithms and this one, what do we call, DP, dynamic programming, right? So we are done with the code. See here, the verdict that we got here is accepted. So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.